Hello, my name is Albert Sosa. Today I'll be going over rotor systems, specifically the types of main rotor systems, types of tail rotor systems, what each system is capable of doing, and some control inputs, what's happening in the flight controls. Um, so most of my information today will be coming from the Schweitzer helicopter pilot textbook, and maybe a couple of things from the rotorcraft flight handbook. So first, I would like to just generally explain what's going on once you're making your control inputs, your cyclic, your collective, and your pedals. So your control links right here coming from your main rotor mast, they come up here and they're connected to your non-rotating swash plate, which is connected to your rotating swash plate. Then your rotating swash plate connected to the main rotor head by the pitch links, and they're in turn connected to your pitch horn, whatever it's called a couple different things. So when you're moving your cyclic, forward, aft, left, right, this non-rotating swash plate is moving all sorts of directions, which will rotate your non-rotated swash plate. So it'll move into its respective position. Now, when you raise collective to change the pitch angle of the blades, this entire thing, moves up or down. So that's what's happening. That's why it allows it to change the pitch angle altogether. So that, in a nutshell, that's what's happening in your main rotor system. The tail rotor is essentially the same thing. However, there's no independent, or there's no. Well, I'll just say that it's a collective movement. So if you take a look at your tail rotor system, your rotating swash plate and your rotating swash plate, they're moving up together, which is why left pedal is more power, right pedal less power. So that's exactly what's happening right there. So also I want to go over the actions of the blade for each system. So there's three. It's feathering, flapping, and hunting or lead and lag. So feathering is something, it goes something like that. So what that does is that's going to change your pitch angle, which will provide your lift, your angle, change your angle of attack and everything like that. So next is flapping, which if my arm is the main rotor hub, it goes up and down just like that, and all that does is that compensates for the symmetry of lift. So your you have your forward airspeed, your retreating blade provides less lift, so your retreating side blade is going to flap down and also, it's just going to provide more lift so it can even things out a little bit. So, hunting, again, it's forward and aft movement, so it'll go something like that. The purpose of that is to compensate for the Coriolis effect. So when you're pulling pitch, um, your blades will start to come. So they'll start to just bend up just a little bit. What that does, it changes your center of mass, and when your center of mass is close to the main rotor hub, that actually causes a blade acceleration. And when it goes back down, your blades decelerate. So they need something to compensate for those forces. As you can see, just in this little drawing right here. So when you start to pick up, your blades will start to change, and you can see that center of mass going slightly in. So that's what's happening there. Okay. Next, now that I mentioned the different types of blade actions, the different types of main rotor systems and what they're capable of doing. First is the rigid main rotor, which only feathers, and the rest of the aerodynamic actions are absorbed through blade bending. Fairly easy system, and it's just blade structure is just it needs to be it needs to be able to absorb all those forces. So the next type of blade rotor system is the semi-rigid, which flaps together and feathers independently, which is actually what we have in the R22. So yeah, just a side note on the semi-rigid system, actually the two-blade system. Um, Actually, I probably should have said this earlier during the cordial split, but the two-blade systems are generally have their blades underslung with respect to the main rotor mast. So what that does is that they are less susceptible to the Coriolis forces. Um, you know, so as you can see here, blades, main rotor hub, center mass on each side, and then you have here the main rotor is slightly to the right, but the center mass remains pretty much the same. The next system is the fully articulated system, which flaps, feathers, and hunts. They're all independent, and this is the type of system you'll find on a helicopter that has 3 or more planes. Your larger aircraft. Okay. Your anatoric systems. Need something to counter the torque caused by your main rotor. So then you have your classic tail rotor with your blades, 2, 4, whatever they are. Also, just some other ones. I've only seen these on Eurocopters, but we'll see. The Fenestron tail. I try to draw it as best I can. All it is, it's a tail rotor inside the actual structure of the aircraft. What that does is it makes it incredibly safe to operate back there, whatever it might be. I've seen it on a EC-145 medevac chopper, which allows to load patients back there and with no harm when you load from any direction. The only downside for that tail rotor is I've heard it's a little weak, but I haven't flown it, so we'll see. The next type of tail rotor system is the actually Notar or no tail rotor, and how that gets its anatoric thrust is from an internal thrust from the engine and the actual downwash from the main rotor system. So here's some of it right here. So you have downwash coming down from the main rotor, and it's traveling along here. It actually used the principal coagulant effect. Also, your internal power source is also pressing or is forcing air out and down, so it actually provides your counter torque. So, just a quick recap. We covered the actions of the rotor system with your different types of control inputs. There's cyclic, collective, and torque pedals. Covered the types of rotor systems and what they're all capable of doing and what their actions mean. So that's it. Thank you.